Next chapter, longitudes and latitudes. Latitudes and longitudes is a coordinate system that is used in locating any point on the globe. But before we dwell into that, let us look at the great circles and small circles. A circle that divides the globe into two equal parts is called a great circle. The center of a great circle is the center of the globe, and its radius is equal to the radius of the globe. Such a circle is the largest possible circle that can be drawn on the surface of a sphere. One can draw endless number of such circles on the globe. All circles following the meridians are great circles, and therefore all longitudes are great circles. Among the latitudes, only the equator is a great circle. A small circle is one that does not divide a sphere into two equal halves. All other latitudes are small circles. Positions of points on the surface of the Earth. The Earth's circumference is nearly 25 miles from start to finish. With the many places on the surface of the Earth, how is it possible to locate one single point? For instance, what if I wanted to tell someone the exact position of the Coronado Bridge in San Diego? It might be hard to describe, but given the coordinates, it should be easier to find it. To find the precise position, parallels of latitudes and meridians of longitudes form an invisible grid over the Earth. Just like a plane coordinate system, we have an origin or zero reference, and we take distances from that origin in two directions. In the plane, the x-axis lies horizontal and the y-axis lies vertical, and both are perpendicular at the 0 point. Any point on the plane is located by how far left or right it is from the y-axis and how far above or below it is from the x-axis. For instance, this point has the coordinates -3,5. The coordinate grid of latitudes and longitudes work in a similar manner. But the problem is that the Earth is not flat, it's a sphere, although even that is not entirely true. The Earth is actually egg-like, bulgy at the equator. But let's work with the idea of a sphere. The x and y axis will not be straight lines, but circles running around the Earth and intersecting each other. The horizontal circle cutting around the center is the equator, and the vertical circle is the prime meridian. But unlike the xy plane, the global coordinates are given in degrees and not unit length. The coordinates of latitudes are the angular deviations north or south of the equator, with the angle measured from the center of the globe. The coordinates of the longitudes are the angular deviations east or west of the prime meridian, and so the equator and the prime meridians are 0 degrees. If you open up the Earth, you will be able to appreciate how these angles are measured. You see, the prime meridian is given angle 0 east or west. At the center of the Earth, if you measured an angle of 30 degrees west of the prime meridian, that line will meet the longitude 30 degrees west at the surface of the Earth. Same thing with latitudes. 30 degrees north of the equator will land you on the latitude 30 degrees north at the surface of the Earth. It's sometimes confusing because longitudes run north-south, but their coordinates are given east and west of the prime meridian. Latitudes run east-west, but their coordinates are given north and south of the equator. I hope you can see why from this figure. And so back to the surface of the Earth, we have the parallels of latitudes and the meridians of longitudes. Latitudes are read first, followed by longitudes. Latitudes are read north and south of the equator. The starting point is the equator, which is 0 degrees latitude. 90 degrees north of the equator is the North Pole, and 90 degrees south is the South Pole. The poles are 90 degrees from the equator, and this is the largest possible angle for latitudes. Longitudes are also called meridians. The starting point for reading longitudes is the prime meridian, which passes through the Royal Naval Observatory in Greenwich, England. On the other side, 180 degrees from the prime meridian, is the antipodal meridian. It is 180 degrees east and 180 degrees west of the prime meridian, and this is the largest angle for longitudes. Unlike latitudes, longitudes are not parallel, and the distances between them reduce towards the poles. Latitudes are parallel to each other and about 69 miles apart. Each degree is divided into smaller units called minutes, and each minute is divided into 60 seconds. So from this, we can give the global coordinates of point A. It lies on latitude 30 degrees north and longitude 15 degrees west. So its position is 30 degrees north, 15 degrees west. B will be 15 degrees south, 45 degrees east. Distance between 2 points along a great circle. The distance between any 2 points on the surface of the Earth is the length of an arc which is part of a circle. Because the Earth is spherical, the distance between any 2 points could be the shortest or the longest. For instance, if you wanted to move from point A to B, you could choose the green path, which is shorter, or take the red path, which is longer. Distance in kilometers. To calculate the distance in kilometers between 2 points along a great circle, we simply find the length of that arc. But first, we need to find the angle subtended by the arc at the center of the globe. Arc length is given by theta over 360 times 2 pi r. The radius r capital of the Earth is given as 6,370 kilometers. Recall that the radius of a great circle is equal to the radius of the Earth. For example, let us find the distance from point A to B, the shortest distance. These 2 points lie on the same meridian. A is 60 degrees north, 36 degrees east, and B is 30 degrees north, 36 degrees east. Considering that the angles are measured from the equator, then the angle between A and B, that is angle AOB, is 60 minus 30, which gives us 30 degrees. So length of arc AB is given by 30 over 360 times 2 times pi times 6,370, which gives us 3,336.67 kilometers. How about the distance BC? B and C now lie on the opposite side of the equator. So the angle BOC is 30 plus 30, which gives us 60 degrees. Arc length is equal to 60 over 360 times 2 times pi times 6,370, which gives us 6,673.33 kilometers. The same is done when calculating the distances along the equator. Consider the distance PQ along the equator. The reference longitude is the prime meridian. P has coordinates 0 degrees north, 72 degrees west, and Q is 0 degrees north, 36 degrees east. The angle POQ is equal to 72 plus 36, which gives us 108 degrees. The arc length is equal to 108 over 360 times 2 times pi times 6,370, which gives us 12,012 kilometers. Next, distance in nautical miles along great circles. Recall that 1 degree is divided into 60 units called minutes, and so 1 degree is equal to 60 minutes. 1 nautical mile is the length of an arc subtended by an angle of 1 minute. Considering that 1 degree is equal to 60 minutes, it means that an angle of 1 degree will subtend an arc of length 60 nautical miles, and therefore the distance in nautical miles between 2 points along a great circle is given by distance is equal to theta times 60, where theta is the angle in degrees. So in our case, the distance AB will be given by AB is equal to 30, the angle AOB, times 60, which gives us 1,800 nautical miles. BC will be equal to 60 times 60, which is equal to 3,600 nautical miles. PQ is equal to 108 times 60, which is equal to 6,480 nautical miles. Having these values, we can find how many kilometers make 1 nautical mile, because clearly a nautical mile is greater than a kilometer. Considering the distance PQ, that is equal to 12,012 kilometers or 6,480 nautical miles. Dividing the distance in kilometers over the distance in nautical miles will give us 1.854. The conventional conversion formula is 1 nautical mile is equal to 1.854 kilometers. Distances along small circles. All other latitudes except the equator are small circles. Their radii are smaller than the radius of the Earth and obviously differ from one latitude to the other, getting smaller and smaller as you move farther from the equator, north or south. Consider this figure. The radius of the Earth is equal to the radius of the equator and is equal to r capital. The radius of the other latitude is smaller and is given as r small. From this figure, OS is equal to OY and is the radius of the Earth, and OY is parallel to CS. Therefore, angle CSO and angle SOY are alternate and are equal to angle theta. From the right angle triangle OCS, cos theta is equal to CS over OS and is equal to r small over r capital. And therefore, r small is equal to r capital times cos theta. The radius r small of a small circle is equal to the radius of the Earth times the cosine of its latitude. For example, find the distance MN. M is 30 degrees south, 72 degrees east, and N is 30 degrees south, 36 degrees west. Angular distance is the sum of the angles, 72 plus 36, giving us 108. Arc length is equal to theta over 360 times 2 pi r, but remember, R small is given by R capital times cos x. So we have 108 over 360 times 2 times pi times 6,370 times cos 30. That gives us 10,402.39 kilometers. Next, longitudes and time. In the ancient days, each city kept their own time, with 12 o'clock being set to noon when the sun reached the highest point in the sky. But as transport improved and people moved from town to town, schedules became confusing because each town had different time, and so there was need to standardize time and make operations more efficient. In 1884, a conference in Washington agreed on the prime meridian as the 0 degrees longitude, and this is the international standard for time. The Earth rotates 360 degrees in 24 hours, and that means every hour the Earth rotates 15 degrees. Considering that 1 hour is equal to 60 minutes, it means that the Earth rotates 1 degree every 4 minutes. A difference of 15 degrees between two places therefore means a time difference of 1 hour. Time zones are based on the fact that the Earth rotates 15 degrees each hour. Since there are 24 hours in a day, there are 24 time zones. Time zones are counted from the prime meridian, which is 0 degrees longitude. The local time on the prime meridian is called the Greenwich Mean Time, or GMT. Local time for other places depend on whether they are in the eastern or western hemisphere. The Earth rotates west to east. All places to the east of the Greenwich meridian are ahead of GMT in their local time. Places to the west are behind GMT. Equally, for any two places on the surface of the Earth, the point to the east will be ahead in time. Points on the same meridian have the same local times, irrespective of their latitudes. To calculate the time difference between 2 points, we simply get the angular distance between them. For example, point A, 30 degrees north, 40 degrees east, has local time 11 AM Sunday. What is the local time at point B, 30 degrees north, 120 degrees east? Both points lie on the eastern hemisphere, but B is further east than A, and so B is ahead of A in time. Let's see the time difference. 1 degree is equal to 4 minutes, and the angular distance between these 2 points is 120 minus 40, which is 80 degrees. 80 times 4 is 320 minutes, which is equivalent to 5 hours, 20 minutes. Because B is ahead of A, we add this difference. 11 AM plus 5 hours 20 minutes will give us 1620 hours or 4:20 PM Sunday. Another example, the local time at town P, 15 degrees north, 25 degrees east, is midnight. What is the local time at town Q, 45 degrees north, 55 degrees west? P and Q lie on different latitudes, but that doesn't matter because time has everything to do with longitudes. The angular distance, one is in the east and the other in the west, so we add the angles. 25 plus 55 will give us 80 degrees. The time difference, 80 times 4 gives us 320 minutes. That is equivalent to 5 hours, 20 minutes. Q is behind P in time, and so we subtract. 12 minus 5 hours 20 minutes will make it 6:40 p.m.
One of the wonderful things about mathematics, I think, is that people are impressed. It's often seen as a very hard subject, and so if you've done math, it's often treated as an entrance requirement, as a credential to do lots of other things. And so one idea is that for example, some MBA programs, the only thing they require going into it is a good, solid math understanding. They can teach you all the business. They just can't teach you the math fast enough. And so I think that math, aside from obvious careers that require math, if you're going to go work in a department that does operations research or something like that, they'll want people with specific skills in mathematics. But math is often seen as a filter or as a screen for many, many other disciplines. And so I guess what I'm trying to say is you can think broad, because math actually is a solid preparation. It's a good credential to go into lots of different fields that people often don't consider at the beginning.